Well, you might think that "there ain't nothing nowhere" is a phrase coined by someone who works in the most abstract field of science, occupying a place somewhere between philosophy and metaphysics. And you'd be right. Professor David Miller has spent a lifetime working in particle physics. It's a rarefied field of research which demands deep theoretical knowledge, heavy financial support, and international collaboration. Now, to help us find out whether some scientists really do set out to learn more and more about less and less, we have with us today 3 A-level students: Natalie Quinn, Amy Winterson, and Simon Coffey, and 3 university researchers: Ian Barry, Rosanna Wright, and Tim Wright. Now, none of us here today, apart from David, is a particle physicist. My interest is in chemistry. Ian, Tim and Rosanna work in laser research, and Simon, Amy and Natalie are studying chemistry and physics. So, David, if you lose us in this discussion, we'll tell you, don't worry.
Good.
But before we get deep into particle physics, perhaps you could let us know how you first became interested in science.
Well, at school, science was one of the things I could do and I enjoyed. But the thing that really grabbed me was what we used to call the third program, where I listened to a program about asymmetries in space-time, the fact that if you reflect the world in a mirror, particles behave differently. And that was a very strange and curious thing that I'd never sort of imagined before, and it was that really caught my imagination.
Yes, I hope we'll be dealing with some of those aspects later, some of these abstract quantities of particle physics. What about teachers? Were there any teachers that influenced you?
Well, our physics master was an extremely laid-back guy, but if you actually showed interest in the subject, he showed interest in you, and it was that way round. Yeah. And he did sort of pick me up and push me along, but it was between lots of different things until this one thing caught my imagination, that I suddenly realized particle physics is not just more and more about less and less, it's more and more about everything.
Yes, well, the title of the programme is "There Ain't Nothing Nowhere," which is alluding to a vacuum, of course.
Yes.
Now, most people, if asked, would say, well, there ain't nothing in a vacuum, but you'd disagree, wouldn't you? And why? What is in a vacuum?
The vacuum, I mean, you can make a vacuum easily. Yeah. I can make a vacuum here by just pumping down this bottle. Right? So there's air being taken out of that bottle, and there's a vacuum inside when I do it. That's not a very good vacuum, but there's no such thing as a good vacuum anywhere in the universe. That's the whole point of the story. That's the whole point of the title. The vacuum is, if you like, the space between stars. But actually there's molecules up there. There's solar wind. There's things blowing about. In fact, as good an example as any of the vacuum isn't going away into special pumped areas or into the space between stars. It's just saying between the nucleus and the electron orbiting round in an atom, that's empty space. And that's really as much the vacuum as anywhere else. Most of what we're made of is empty space. And if you want to know why, just take an X-ray picture. The X-rays go straight through because it's mostly vacuum. And yet vacuum isn't empty, and that's really the point. Even the most perfect vacuum, where you've taken all atoms away, you've got in between the atoms, you've got in between the electrons and so on, what's there? Well, there's lots of things there. There's forces there, for a start. For instance, the electrostatic force we're mostly familiar with, and you've probably all played about with this trick. Let's see if it works. If I put that comb down there, I pick up the pieces of paper with the comb that I've electrified just with my hair, and that's an electrostatic force reaching out over an inch or so.
And acting through a vacuum?
Well, it's acting through the air, but the air might as well not be there. If we need the air to breathe, but if this was a vacuum-filled studio,
it would still work.
It would still work. The thing would still pick up, because that's a force working in space. And these forces working in space are amazing things. I mean, the human race took a long time to get the idea of a force working in space. There's a couple of magnets here. If I bring that magnet slowly towards that magnet, whoops, it moves away, because I've got like poles. This is magnetic field. If I put the unlike poles together, they'll stick. If I put the like poles together, they push apart. And that's a perfectly well-known thing. Yeah. Or I could even show the magnet actually moving a compass needle around like that. And it's acting over quite long distance. I mean, the compass, that's actually pointing the way it is now. If I take those away, pointing the way it is now, because it can feel the Earth's magnetic field, which is acting over thousands of miles.
And that magnetic field would still act in a vacuum?
Well, yeah, the presence of the air makes no difference at all to that. It's just acting through space, through the vacuum. And the other thing, of course, that acts through the vacuum is gravity.
Yeah.
Gravity doesn't just make this ball go up and down here. If I threw this ball at escape velocity, it would go into orbit around the Sun, but it would still be orbiting the Sun like another planet. And that's gravity acting through the vacuum. Now, it took the human race a long time to figure this out, that the vacuum, even between the planets and between the Sun and the Earth, and for satellites now we know going around the Earth, all of this, there's a force acting through empty space. We know it's a force. If I take this sock with my golf ball in it, right, you can see that if I pull the sock and put a force in it, then it stretches. So if I swing the sock around slowly with the golf ball in, then it's a certain length, and I swing it faster, it stretches out. And that is essentially what's happening when the Earth swings around the Sun. The force between, the gravitational force between the Sun and the Earth is acting like the stretched sock and actually constraining the Earth to stay in a circle. And that gravitational force is acting through the vacuum of space. There's a little bit of solar wind and stuff there, but that doesn't matter very much. That gravitational force is actually a force in the vacuum. Now, it took the human race, as I say, a devil of a long time to figure that out. It was only in when? The 16th and 17th centuries, when, first of all, Tycho Brahe, then Kepler came out with his laws. I think Copernicus was involved, and then finally Newton realized that you had to have this totally new concept of a force acting through the vacuum. And all of this actually, if you're interested, is explained in a super book by Arthur Koestler called The Sleepwalkers. It's one of the best books of popularization of scientific history that I've ever seen. Anyhow, that is the beginning of this concept that the vacuum is not empty. There ain't nothing nowhere, there's fields in the vacuum.
Yeah, I can see it written all over Amy's face. What's this got to do with particle physics?
No, my question was, if there's no such thing as a perfect vacuum, how on earth, one, did we know there was such a thing as a vacuum, and two, if we calculate things, you know, the speed of light travelling through a vacuum, but if it's not a perfect vacuum, how on earth did we work it out?
Well, the other thing that was happening around about the 17th century is that people were suddenly realizing that there were ideal, simple ways of doing calculations. Until then, nobody had realized, for instance, that when you slid something on a table, that in fact it was trying to carry on without any resistance, and then the friction was slowing it down. And people like Galileo and Newton actually realized that there are some very fundamental, simple ways of looking at things. And the world we live in is always slightly more complicated, and things stop it being as simple as it might really be if you could strip away all of the other effects and look at one effect at a time. And I think the vacuum, as we're talking about it now, is in that category. The vacuum is the absence of other things. And you can either go deep into space, or you can pump away and try and make a vacuum somewhere. It depends on what you want to do, how good a vacuum you want. But if you're just going to think about it, all you have to do is think about a space without any objects in it. That's the vacuum. And that's the sort of mode of thought that really came about in the 16th and 17th centuries for the first time, when in particular Galileo and Newton imagined things with all the inessentials stripped away and took the effects one at a time and thought about the fundamental science. And that's what you're learning about when you learn sixth form science, isn't it?
But again, I go back to the question, what's this got to do with particle physics?
Okay, well, the forces that are acting through the vacuum, like that one, making those pieces of paper jump up, and the magnetic force here. Let's take that, the electromagnetic field acting through the vacuum. We've got to ask, what's carrying that force? And it took people a devil of a long time, 200 years or more after Newton, before they began to get even the first thought of what might be carrying that force. What we now think is carrying that force, either magnetism or the electrostatic field, is actually photons. Photons like the photons of light that we're seeing each other by. But not quite the familiar everyday photons that we see with. What you've got to think of is virtual photons, photons which, say, around this magnet, there's a little field of photons which are sitting there in a sense. There's a fixed magnetic field. I can see it if I bring my compass up close. And those virtual photons are out there in the space, and you can feel their influence when you go close. Why do I say that? Well, I say that because the mathematics works out that way. It was Maxwell's equations and then quantum mechanics and so on, all very connected step-by-step thinking. We had to say that it was virtual photons, but that's a desperately difficult concept. Yes. I mean, what the devil, I mean, the word's fine, virtual. It's not the same as virtual reality. Yeah. Virtual reality is something that you were sort of worried about here, isn't it? A virtual photon isn't just something that you see in a headset.
Yeah, I was wondering whether it was maybe something similar to virtual space, which is something that exists only as a pattern.
Well,
not in reality.
Well, these photons really do exist in the space we live in. And if I had, for instance, a strong magnet, then I might try and convince you that the virtual photons are actually there inside the strong magnet, just as I'm saying the virtual photons are around here. Let's take an example from the Daresbury lab. Now, I believe, Tim, you actually do experiments at the Daresbury lab. Now, if we take an example of the Daresbury lab, this is the Daresbury lab. It's in Cheshire. It's a place where various experiments. They used to do nuclear physics here, and that's the tower that people see from all over northern Cheshire. But this thing here, you can't really see it very well. Under that L-shaped building is a ring of magnets. And that ring of magnets is actually a place where they send electrons around in circles. Here's a picture of the inside of the ring. You can see a little bit of the feeling of curvature. This is one of the magnets that does it. The beam of electrons going round in a circle goes on round here. And you can see here something coming off tangentially, a tube, and a thin window. It's actually just a foil of some kind. And because, as I say, material is largely transparent to X-rays, the X-rays that come out go straight through that foil. If you like, that foil is very little different from a vacuum to the X-rays, though one or two of them will scatter. So the ring looks like that. There's a ring of magnets, and standing off at a tangent to the circle, all the way round, you've got what are called beam lines, where people take a beam of X-rays and try and do something with them. They might try and make simple images. More likely, they'll try and scatter them off crystals of materials. You actually work with vacuum ultraviolet beams, which are lower energy and longer wavelength version of the same sort of thing, also coming out through the windows from that machine.
Sure.
Yeah.
How do you generate those beams? Because you said the electrons are circulating around.
Yeah. To make the electrons, to get them up to the energy you want, you actually, as well as having a ring magnet with a fixed magnetic field given by an electromagnetic current, you also have to have a radio frequency oscillator. And as the electrons come through it, they get an extra kick, and they go faster and faster and faster. And as they go faster, you raise the fixed magnetic field. You increase the current in the magnet. And so that's why it's called a synchrotron, because they synchronize the increase of the magnetic field with the acceleration of the particles from the radio frequency. And so this synchrotron produces the X-ray and vacuum ultraviolet beams, which are called synchrotron radiation, because the particles lose their energy in the magnets that are needed to make the particles go around in a ring. So you can't have a synchrotron without some synchrotron radiation, because what's happening is that the electrons going around in the synchrotron are actually hitting the fixed virtual photons in the fields in those magnets. And as they do it, those fixed virtual photons are getting knocked out as real X-rays. And it becomes something like what I can show you here on the floor. If these ping pong balls are regarded as the virtual photons sitting there fixed in the magnetic field, and this daft coloured golf ball is the electron coming around. Of course, there are millions of electrons actually in the bunch that goes around, but the electrons are coming around and they're bumping into the occasional virtual photon in the field. And when they do that, the photons scatter on forwards, and that is your beam of synchrotron radiation. Those are your X-rays that come out, or your vacuum ultraviolet for your experiment.
Do they always go in the same direction as the electrons? Or can they go in all sorts of directions?
Usually pretty closely tangential to the electrons. There's a little bit of sideways movement. But this, to me, I mean, it is a very deep idea, the idea of virtual particles in the vacuum. This, to me, is about the most graphic illustration of just how those virtual particles are there. They're real. They're not just an imaginary pattern, which is what you're feeling the word virtual means. Yeah. They're real things, and we hit them with electrons, and we turn them into a real beam, and that real beam is very useful. You do experiments on it. Other people have done experiments on this as well. The scattering from crystals, in fact, is extremely important in all sorts of things now, and I think that's going to turn into a picture. Ah, that's the picture. This is, first of all, what's happening in there. The electrons flying around inside the magnet and coming off tangentially. We've got our ping pong balls, which are real X-rays. So the fixed magnetic field in there is knocking out the real X-rays, and that's what we do experiments with. And if we then put a crystal out here and we scatter off it, then we can predict all sorts of lovely patterns, and this is one of the most exquisite patterns. This is scattering predicted from a protein crystal, a very complicated molecule which has been crystallized, and then an X-ray beam from Daresbury would be shone at that, and you would try and detect, with beautiful detectors, you'd try and detect this pattern.
And the aim would be to determine the structure of the protein.
Yeah, because this is becoming more and more important. You noticed how many beams there were on that picture. This is becoming a more and more important part of modern science, just to go to one of these machines and scatter these beams from things. And one of the things that they've been able to do, for instance, is to reconstruct what a complicated living thing looks like. And I think we're going to have, that strange and complicated thing, very beautiful, is actually a very nasty thing. That's actually, I believe, a foot and mouth disease virus reconstructed by using the sort of X-ray scattering that they do at Daresbury. Now, I'm telling you about this not because we're talking here about foot and mouth disease or anything like that, but just to illustrate this virtual particle in the vacuum, which is a very abstract idea, a very difficult idea to get hold of, actually has reality. You can knock it out and turn it into something real, and it has usefulness.
Right.
And so, you know, we're trying to get to know more and more about everything, not about less and less.
Forgive.
But the thing that follows on from this idea that you've got the virtual particles in the vacuum, these are virtual photons. They're particles without mass, so that the vacuum will very easily support virtual photons because these are particles without mass.
Are they moving?
Pardon?
Are they moving?
They move if I move the magnet. It's very hard to say that they're actually, it's a very complicated idea, whether they're moving in the field. If I come in and hit them, I've got to regard them as already there.
My understanding of a massless particle is that it's moving at the speed of light.
Ah, but these are particles with imaginary mass.
Moving faster than the speed of light, then?
No, they're just already there when you hit them.
All right.
Natalie?
When the electron hits the virtual particles, the mass is created, their energy is created. Does that come from the energy of the... So the electron loses energy and it's given to
the X-ray that was made is still a real X-ray, and that means actually that's a photon, like a photon of light. It happens that they have no mass. So that all that's happened is the energy of the incoming electron has altered the imaginary mass of that virtual particle into a real photon which has zero mass.
But photons have energy.
Photons have energy, yes.
And energy is mass. According to Einstein.
Energy
equals mc squared.
Well, there's two kinds of mass. There's two kinds of mass, if you want to talk about it. There's the sort of mass a particle can have, like me, just sitting here, all heavy on the stage, and like you, okay, we've got mass when we're sitting still. If we were travelling at enormous speed, we'd actually be heavier, because we'd have the mass due to the extra energy we have. Now, real photons, like photons of light or photons of X-rays or gamma rays or any of those things, turns out that you can't make them sit still normally. The ones that are sitting still there have to have the wrong mass. They've got to be imaginary mass. They're funny things. But a real photon has always got to be moving because it doesn't have a rest mass. If you bring a photon to rest, all its energy is gone. It only has the mass due to its movement, due to its kinetic energy. So it's a unique particle. It's a very special thing.
It's a rather bizarre concept, this virtual particles. I mean, who actually thought of the idea? And why did they come up with such a bizarre idea?
I don't know who used the word first. It's one of the things that bubbled up from quantum mechanics in the 1930s. As quantum mechanics turned from being a description of atoms and the binding of particles in atoms, then Dirac came up with the idea of particles and their antiparticles, and then you started to have a theory of how all of that worked, and the only way you could make that theory work was to allow the field to be carried by virtual particles. And then you had to have actually lumps in the field. This is quantized fields.
So this is more like a consequence of the theory, the existence of the virtual particles?
No, the theory is a consequence of the world being like that.
Yes.
So the world is like that, and we try and come to grips with it. And what we have to come to grips with then is this idea of there have got to be virtual particles to carry the forces over a distance. And they're in the vacuum.
Simon?
If these virtual particles aren't moving, then what's happening when, say, two magnets interact? How do they exert the force on the actual magnet?
You've got to regard the virtual particles as somehow having been got out there. But if you try and follow them out, you'll end up with nonsenses.
But, right, originally, there's virtual particles in a vacuum. So it's not really a real vacuum. There are actually things in it.
It's full of things.
But just to confuse things. But when you put an electron in or something and you move, like you showed with the ping pong balls.
Yeah.
But if they weren't moving in the first place and you started them moving, do they stop or do they continue until you do something else to them?
They start obeying Newton's second law. They carry on until you do something else to them. They carry on. Once you've got a real particle in space, the only thing that will deflect it is the forces in that space. Now, there might be electrostatic forces, magnetic forces, gravity. It'll follow those forces and it'll have a trajectory.
But this is really only theory, though, isn't it, to be honest?
No, I mean, we do the experiments. This is what we see.
Proved this.
This is all absolutely everyday in the lab stuff, and it's needed to explain the way the world works every day. So that although it sounds abstract, it's driven by real observation. And then you have to go through the mathematics, and then you've got to try and find some pictures that explain it, and this is what we're trying to do. Now, the funny thing is that you can go on beyond this. Once you've got this idea of forces in the vacuum and the virtual photons, turns out that inside the vacuum, if you've got enough concentration of energy, not just the amounts they use at Daresbury, but much more, then it turns out that you can find whatever particles you can think of will be there, producible out of the vacuum. They're virtually there.
You just need enough energy.
You just need enough energy, or you need the right conditions.
Yeah.
So that as well in the vacuum, I can think about it as sitting there, having just empty space, not even any fields around much to talk of, and yet I can imagine that an electron and an anti-electron, a positron, might appear and move and disappear. And they are, in principle, an electron and positron are there in the vacuum all the time, everywhere, popping up and disappearing.
So the vacuum is seething with activity.
It's seething with activity which we don't notice.
Yes, it's imperceptible.
It's imperceptible unless the right things happen. Now, Stephen Hawking, for instance, came up with an incredible picture of what happens when you look at the vacuum on the edge of a very small black hole. You know what happens around black holes? The gravity field gets very, very strong indeed. And so these imaginary pop-up and disappear electrons and positrons, which normally don't matter, we normally don't notice them. Those things, on the edge of a very strong black hole, they'll go apart a little bit and come together, and while they're trying to do that, they move far enough apart in the strong gravitational field that one of them falls into the black hole and can't get out, and the other one gets away. And this is known as Hawking radiation. It's not been observed yet, but it's a very profound idea from cosmology, that perhaps small, strong black holes actually fill themselves up by sucking electrons or positrons out of the vacuum and squirting others away from themselves. This is one of the really far-out applications of it. Now you might say, why can, out of nowhere, particles and antiparticles appear and disappear? You've heard of the Heisenberg uncertainty principle.
Nobody say, we're not sure.
Has everybody heard of the Heisenberg uncertainty principle? The Heisenberg uncertainty principle is the bank manager principle of physics. You know that a bank manager, if you're an ordinary person, not a Greek millionaire, you go to a bank manager and you say, can I borrow £100,000 because I'm buying a new house? And he'll say, I'll let you have it for a week as a bridging loan. If you got the same bank manager and say, can I borrow £1,000 to help me buy a camera? And he'll say, you can have that for 2 years. So the more you want to borrow with a bank manager, usually the less time you can have it. And Heisenberg's uncertainty principle is a very similar principle for the vacuum. If you want to do something in the vacuum where there isn't any special energy lying around, like make an electron and a positron pop up. Now those things have mass, so they've got some energy. They can pop up virtually in the vacuum and disappear again, as long as they do it very quickly, very temporarily. And so this is how the vacuum can be filled with all sorts of seething things that you're not aware of, but you wouldn't notice them unless you're doing something that's energetic enough to excite that particular property of the vacuum.
So the energy's got to be there.
In order to see them, the energy's got to be there. Mm-hmm. But actually, in principle, they're there all the time. That's one of the funny things.
Can you say quickly, what sort of timescale were you talking about then?
Well, it's just given by the magic number of quantum mechanics, the Planck constant. Mm-hmm. So it's just, if the energy is borrowed for a time t, then the product of the borrowed energy, the wrongness of energy of a particle, and the time that it exists is approximately equal to Planck's constant, which is a very, very small number.
And what's that in time for, say, an electron and an anti-electron and positron?
For an electron-positron annihilation, you're talking about, I don't have that off the top of my head.
Yeah. It's very, very quick, presumably.
Yeah. Can't do it straight off the top of my head.
Neither can I.
I thought Heisenberg's uncertainty principle was about you not being able to define position and momentum simultaneously.
That as well, yeah. That's because we live in a four-dimensional universe, Mike.
I thought, yeah, right.
You remember, space and momentum it's about, but if you go into the fourth dimension, it's energy and time.
That's right.
And it's the same relationship.
Yeah.
Yeah. It looks different, but if you go into the fundamental level, then in fact energy and time, or space and momentum, turn out to be the same relation.
So it's just an inherent that you can't determine an energy and time in the same amount of energy.
Yeah, that's the same sort of
and
thing.
what you're saying is you can have lots of energy, providing it's so short-lived, it's for just a short period.
Now, the research group that I work with, we actually work at a place called CERN in Geneva, where the energy is a lot higher than they get at Daresbury, because we're trying to excite these things. We have this great ring, which is 27 kilometers in diameter. That's Geneva Airport, to give it a scale. And that's the Franco-Swiss border. And at these intersection points here, one just off the picture, that's where electrons and positrons at very high energy collide in a tiny point of space. Something much smaller than an atomic nucleus is the space in which they collide. And when they collide head-on, then there's an enormous amount of energy just concentrated in one point. Now, at one of our experiments, the dotted line, of course, is drawn as if on the surface. But if we go to the actual experimental area, ours is just off here, and there's a lift there. We go down 100 meters from that lift into our actual experimental area. And on either side of our experimental area, there's this enormous tunnel. This is a magnet very like the one that we saw at Daresbury Lab. And you can see a very slight curve. The tunnel is curving away. It's 27 kilometers in diameter. And the electrons and the positrons zoom around here, and they meet inside our experiment. And they meet in this tiny little volume right in the center of our experiment, right in there. And when they collide, essentially that piece of the vacuum gets pumped up to an enormously high energy density. It's not an unprecedented energy density because, of course, in the Big Bang, there were even higher energies compressed into one tiny space. But in a sense, we're getting back further into the Big Bang than anybody else has been by doing this. So, whoops, can we go back to the first one for a second? Not ready to change, yeah. So this one here, what we've done is we've made that collision, and we've made it at an energy where, in fact, the electron and the positron came in, they annihilated, and at that point in the vacuum, they made a particle called the Z. And the particle sat there for, I do know the time for this one, I couldn't scale it quickly enough for you. That sat there for 10 to the minus 25 of a second. That's 1 upon 10 with 24 zeros after it of a second. It sat there, and then it blew apart because it has so much energy. You know, its mass is actually equal to the mass of an iron atom, which is an atom with 26 electrons and 56 protons and neutrons. But that's actually a very fundamental particle. As far as we know, it's as fundamental as the photon that we were talking about earlier. But it's much, much more massive.
By fundamental, you mean indivisible. You can't get any smaller than that.
Not just that. The photon and the Z have something else in common. They actually carry forces. Yeah. Now, the photon is a massless particle that carries forces, and that's why I can do this. And because the photon is a massless particle, it can get out into space a long way with only a very slightly wrong energy, according to Heisenberg, and you can reach out an enormous distance. And that's why the electromagnetic force reaches out a long way, because the photon's a massless particle. This Z actually is what causes some nuclear decays. It causes, actually, it's its brother that causes the nuclear decays, but it's part of what's called the weak interaction. And the weak interaction is something with a very, very short range indeed, because the Z is very heavy. The brother that causes beta decay is the next picture. If we look at the next picture, here we've now raised the energy of the machine in the last 2 years, and we're now making pairs of these other particles, and one of them decayed into these two jets here. The other one decayed into a particle we saw up there, and something we didn't see at all, but the computer has drawn in the balance. That's a particle called a neutrino that we didn't see, but since everything else was balanced on this side, we knew some momentum had to go off that way. And that neutrino balanced it up. So there's a W decayed into two things like that, and another W went like that. Now that W, or one of those W's, is actually what causes nuclear beta decay. It's what causes wristwatches to glow and all sorts of things like that.
Natalie, you're champing at the bit.
So you said that the neutrino carried away momentum?
Yes.
Well, in mechanics and physics, we'd always been taught that momentum equals mass times velocity.
Yes.
But the neutrino is a massless particle, isn't it?
Well, the neutrino is like a photon as far as we know at the moment. It might actually have a little bit of mass. But when you start getting up to particles which travel close to the speed of light, then we've got to start using Einstein's language, which is relativity. And in relativity, particles which don't have any intrinsic mass of their own, when they've got an enormous amount of energy, they can carry momentum with that energy. And that's, some people call that the inertial mass of the particle. It can have inertial mass even though it hasn't got any intrinsic mass. So this is just a consequence of relativity? It's a good question. Neutrino is a very awkward object. We still haven't sorted out what's going on with neutrinos, but that's not what I'm talking about today. What I'm talking about today is essentially saying that when we put enough energy into a point in the vacuum, then we find there's all this wonderful complication. And, okay, this might just be fun, but one of the things that came up in about in the 70s, is that if you put that much energy in the vacuum, you make these heavy particles. They're as fundamental as the photon, and yet they're very heavy. Why are they so heavy? And theoretical physicists scratched their heads about that, and a number of them, including Tom Kibble at Imperial College and Peter Higgs, who's now at Edinburgh, thought of a way of explaining how the W and the Z got their mass, and they get it from the vacuum.
Are we all with that?
This is one of the most curious ideas around in physics at the moment, that particles actually get their mass by moving through the vacuum. We got so excited about this that we said, we've got to have, I'm afraid, to the government, to really prove this, and it's got an enormous amount to do with the beginning of the universe and the Big Bang, and it explains beta decay, it explains all sorts of science, and we really must do the experiment to prove that this is true, and that means we're going to need another, even bigger accelerator. And the science minister at the time, William Waldegrave, said, convince me that this is worthwhile. For instance, he said, can any of you put on one side of a sheet of A4 paper a description of this effect in the vacuum, which I can understand? And so we had a competition. And the bottle of champagne that I've been waving at you, I actually won from him, because he said he'd give a bottle of champagne to those who could actually do this. And he claims that he understood my explanation.
Are you going to share that explanation with us?
Yes.
Hang on to your seats.
My friend Chris Llewellyn-Smith at CERN actually had this redrawn as a cartoon. So what I want you to imagine here is a room full of party political workers. They have a slightly blue tinge, as you'll see. And they've got a cocktail party. They're all standing around drinking and just chattering away at each other. They're all uniformly distributed just as a sort of lattice across the room. And at a certain moment, a distinguished ex-leader of their party, an ex-prime minister, comes in. And as soon as she comes in, people notice her, of course, and they begin to cluster around her. And as she moves across the room, the people who were over at that side go back into their sort of open distribution, and the ones here are clustered around her. So as she moves across the room, she's always got a cluster around her. And this means that she has acquired, in some sense, extra mass from the clustering. That means that as she sort of pushes across the room, in a sense there's more force on the floor to move the little cluster of people around her. And as she slows down, there's more force on the floor to slow her down. She's got more momentum just because of the clustering.
This is a vacuum then?
Well, in a sense, this will be the vacuum in one step or two on. Just hang on a moment. This is a far-fetched picture of it, but it's actually based on something that condensed matter physicists, people who worry about electrons moving in crystals, would recognize. Because the people who talk about electrons moving, say, in silicon, say that as an electron moves with an electric field around it, the silicon atoms cluster slightly around the electron, just because of the attraction between the negative electron and the positive atoms in the lattice. And that produces, due to a sort of pulsation around the electron, it actually makes electrons, you put an electric field on and try and get them to move, they seem to have many times their normal mass. They actually acquire some of the mass of the lattice and seem to carry it with them. So this, although it's a daft explanation in terms of the particle-political thing, is actually a piece of good solid-state physics. The theory of that is well understood, and people know how to make that work in solids, in a lattice. What Tom Kibble, Peter Higgs, and people like that did was to take that and apply it to the vacuum. And they said, let's imagine a new field in the vacuum, not electrostatics, not magnetism, not gravity, a new field in the vacuum, which has become called the Higgs field, after Peter Higgs. And let's imagine that when a W or a Z moves through that field, the field in the vacuum clusters around and gives it extra mass. And they worked out that they could do this mathematically. It was allowed. Even though now we're talking about not a crystal, where you can see what's doing the clustering, we're talking about the vacuum, empty space. And you're putting something new into it, a field, which is going to cluster around some of the particles as they move through. Now, Chris Llewellyn-Smith, as well as getting these diagrams drawn, thought of an extra refinement to my picture. He said, what happens if Tony Blair came into this room? Someone of the wrong persuasion. Of course, there'd be no clustering around him at all. So he's like a photon moving through the vacuum. This new field that Higgs invented interacts with the W and the Z, but it doesn't interact with the photon, and that's why it doesn't pick up any extra mass. And that's why it has long-range forces. And the W and the Z, which are very heavy, can only get away. Heisenberg only lets them go a very short distance before he pulls them back, whereas the photon can be out there over large distances very easily.
But particles have got different masses, haven't they? They don't always have the same mass. So how do different particles pick up different degrees of mass?
This is the level at which we don't know. We don't know why some particles have different masses. Our present model has, I think, 18 or 19 numbers in it, which we have no idea why. And some of those numbers are why is the W the mass it is, why is the Z the mass it is. We're going one step at a time, as science always does. Right? So the step we're trying to do at the moment was trying to see whether this Higgs field is a sensible explanation at all. It's a nice abstraction, but is it actually going to do anything for us? Can we test? I'm an experimentalist, I'm not a theorist. Can we actually do an experiment to see whether it's there? Well, I think we can, because if the Higgs field is real, something else might happen in it. Now again, we're back at our party political crowd here, and you notice at this point somebody's about to appear and launch a rumour. Perhaps he's denouncing this guy over here for being paid £1,000 to ask a question in Parliament or something. There's some sort of rumour being launched into the room here. Now, of course, the moment the rumour is launched, the guys here begin to cluster and tell each other the rumour. And the rumour will move across the room towards the fellow who's the subject of it. Now, again, you might think this is daft, but that rumour, that clustering, that information which is causing the people to cluster, is actually generating spontaneously some extra mass. There's a massive particle moving across the room, which is the clustering. You don't actually need an attractive object at the center. The clustering itself can generate the extra mass. And that again is something that happens in condensed matter physics. You can get things called dilatons or phonons, ballistic phonons, which travel in a straight line through a crystal, just like a particle. And because there's a vibration and the things get closer together, they can have an effective mass. Now, once you've got this field that Higgs invented, if it can pulsate in itself, then it might generate little pulsations which have got mass. And those pulsations would be what we call the Higgs boson, the Higgs particle. And we might be able to make that particle in the lab. In fact, this is our big quest. This is why I won this bottle of champagne from Mr. Waldegrave by this daft story, because we're trying to persuade people that it's a sufficiently interesting and important thing to actually find this Higgs boson, because if we find it, then the Higgs field will exist, and if the Higgs field exists, then we know that we have an explanation for the fundamental forces carried by these heavy particles, the W and the Z. So this is the quest. And this is the stage we've reached now. I had a student who completed his PhD 2 years ago who failed to find the Higgs boson. And you'll find a lot of theses at the moment from students working at the LEP machine at CERN at the moment, where we're failing to find it, but we're pushing back the limit step by step. What we want to do in CERN, in the same ring, is accelerate not electrons but protons. Now, protons being heavier don't lose so much energy by synchrotron radiation, so we can get up to 70 times the energy. And then we think we're almost sure to find the Higgs boson if it's there. If it's there, I mean, it's all a hypothesis, so we can't be sure that we'll find it in any particular place. And if we do, then the events would look something like this. Now here, this is a much more complicated picture than the ones I showed you before, because the red tracks, this is a computer simulation, we haven't done it yet. The red tracks here are three things from a rather simple decay of a Higgs boson that was produced at the center. All the other tracks are the rest of the bits of the two protons that were required to collide. Electron-positron collisions are nice, simple things. Protons are nasty bags of objects. It's like colliding two bags of potatoes. The potatoes flying everywhere, but perhaps two of the potatoes that collide will actually coalesce and form the Higgs boson. And we know that with the machine that we're trying to build now, then we ought to be able to actually see these things. If we prove that they exist, then we prove that the Higgs field exists. If we prove that the Higgs field exists, this is an extra thing that's got to be in the vacuum everywhere. And it turns out that it's not just the mass of the W and the Z that get dictated by this field. It's the mass of all the other particles, the electrons, and the quarks, the things that come out when the protons collide. All of those things actually get their mass from moving in the Higgs field.
What actually is the Higgs field?
Well, it's just a field that fills space. It's a presence.
What happens to all these masses that group together, like when you had the rumour going across and all the party-political people joined together, and then it starts to move across the room? What eventually happens to that? Does it just keep growing, or?
Well, it's like ripples. If you imagine, say, the surface of water, it's like ripples. You know, ripples can sometimes be all together, or they can dissipate and spread out. And it's something like that. It's a dimple.
So it keeps growing
space.
and then it dies out.
Yes, it'll. But when it's propagating as a particle, then it'll have a certain coherence, just as any other particle. Because you know that in quantum theory we describe any particle as a wave, as a sort of a fluctuation in a field. And that's all the mathematical part of it, but there's always a picture attached, and the picture is of a sort of dimple in space.
But if enough of these come together, if the cluster keeps growing and growing, if anything like that happens, what do you think would happen next? Or is that physically not possible?
Each cluster, just to conserve energy, the cluster would have a fixed size given the amount of energy you put in. You've got to put in a certain amount of energy, you'll get a Higgs boson of a certain energy. It's apparently got an intrinsic mass of its own, if it's the sort of Higgs boson that Higgs wanted. And so that intrinsic mass of its own is what we would measure here. Now, it might turn out that it doesn't exist like that. It might be more complicated. We've got to go to a high enough energy to be sure that either it is there and we can recognize it, or whatever is there instead is beginning to show its effects. Because this thing isn't only important now to explain the interactions happening now. It's even more important, if it's there, for what it tells us about the beginnings of the Big Bang. Now, one of the things that astronomers have been observing for years is that if I look at that side of the universe, and if I look at that side of the universe, and if I look for photons again, just coming out of the universe, then actually they can see the afterglow of the bang, the flash of the Big Bang. It was originally a very bright flash. It's been cooling down ever since, because the universe expands, and whenever anything expands, it cools down. There's photons coming from over there, and there's photons coming from over there. They're both at very low temperatures, and they're at exactly the same low temperature, irrespective of which direction they come from, to within 1 part in 100,000. There are very slight variations at that level, which are very interesting. But how did the universe over there know that it should be at the same temperature as the universe over here? They've not been in touch, as far as we know. In a simple model, they've never communicated with each other until these photons arrived and met at the Earth now.
But they started in the same place, so...
No, they didn't start in the same place.
Didn't they?
No, the Big Bang is a great big extended thing. You're looking out in two opposite directions. They think they've been travelling in a straight line. There's no way that they think they were in the same place.
But equal and opposite, though. I mean, if you're saying they went in opposite directions,
they're coming in. They've been coming in ever since. You can think of it as just an envelope. Right out there, there's something like a great big fluorescent light covering the surface, but moving away so fast that the light is Doppler shifted like the sound from an ambulance, you know, so that it's lowered in frequency so much that it's very, very cold now. And those photons have never met each other before in their lives. And that little bit of plasma up there never knew about that little bit of plasma within the picture that we can see.
But didn't they start off in the same place?
Well,
yeah.
if they can have started off in the same place, then that would solve the problem. But how could they possibly have started off in the same place if what we see now is a universe that's once blew up and is just gently slowing down, if at all? Those guys, within the bit of the universe that we can see now, there's no explanation of it. What some clever guys thought of about 10, 15 years ago is that they could explain it if they've got something like a Higgs field in the vacuum. If, in fact, when the universe first formed in the Big Bang, it didn't just bang and then go out like this. If, in fact, what it did was it started, and after quite a short time, when it was all nicely sort of communicating with itself, extremely hot, extremely dense, if something dumped energy into it and made it go, it's called inflation. This inflationary theory of the universe says that somehow the stuff that was around got blown apart even faster than you'd expect from any physics we know now. And one way that they found of doing that is to have a background field like the Higgs field in there. And that background field somehow dumps its energy and rearranges itself. And while it's rearranging itself, it blows the universe up. So if we prove that the Higgs boson exists, that means we've proved that something like the Higgs field exists. Then we've proved that these really far-fetched theories about how the universe can be the way it is, one more step in them could be true. You could have this background field which started off at the beginning of the universe, rearranged itself and blew things up. And at that point, ever since, everything's been slowing down. So that literally, since the time minute fraction, 10 to the minus 10 of a second after the beginning of the Big Bang, these two bits of the universe didn't know about each other. But before that, they were together, and they blew apart.
That was really high energy and very dense.
Oh, yes. I mean, the stuff we do at CERN, even what happens here, is negligible compared with the energies that would be involved there. And that's why I don't say it's necessarily the same Higgs field. There's got to be a lot more physics between the level we know about here and the level that happened at the Big Bang. But if we know that the Higgs particle exists, therefore the Higgs field exists, then it isn't stupid to start talking about these fields which fill the universe and which can pump energy back into them. In fact, it's the natural thing to do. And that's, in a sense, at the moment, the reason for this program. You know, it's not just because we want to find out how the forces work. It's not just less and less.
Yes.
More and more about more and more, Mike.
Yes. I mean, you're going to answer, what are we doing here? How's matter created?
Well, any scientist can only answer the questions that can be well posed.
Yeah.
And there are a lot of questions that all of us think about that just aren't well posed as scientific questions. What I'm trying to convince you of is that some of these really far out things are well posed scientific questions. They're not just speculation. And that's the important thing to any experimental scientist, I think.
When you said the Higgs field rearranges, doesn't that imply that there was some communication between bits of the field? And what carries that communication between them? How can the field actually rearrange?
Now you're starting a different story.
That's an extra.
And it's a very good question for condensed matter physicists, because if the Higgs field rearranges itself in some little domain of space, then one domain of space might rearrange itself one way, but another domain of space just a little bit further off might rearrange itself a different way, and they might not have time to communicate. And this becomes like something that happens when, for instance, iron is cooled down. And, you know, iron, when it's warm, is just sort of disordered. If you cool iron down, it breaks up into little domains, each of which has its own magnetic field, and it needn't be in the same direction. And in the same way, our universe probably all has the same Higgs field arranged one way. There could be, out of sight, beyond our horizon, other universes where the physics is different, where the Higgs field rearranged itself differently. As far as we can tell, we can't communicate with those.
David, just spend the last couple of minutes telling us, or I'm going to ask you, what's the future of particle physics? Where's it going? I mean, you've given us a good idea.
Well, it's an experimental subject, so you can't jump too far ahead. You can only say, what's a well-posed question? Yeah. The well-posed question for us now is, can we find the Higgs boson?
And when you found it?
When we found the Higgs boson, is it behaving in the simplest way that it might do? Or is there more than one of them? Because generally scientists tend to invent the simplest theory they can to explain anything. But once we've got there, there are some gorgeous theories that we'd quite like to believe, but daren't, which say there could be more than one Higgs boson. Now, if it turns out there's more than one, then that gets us into a class of theories, perhaps, which might also, for the first time, tie gravity in with the rest of physics in a way that we can understand. So that would be very exciting as well. But that's a hope rather than a promise. I can't promise you we can do that, because it'll depend what's there when we get there, as for any science.
Yes, you can't promise any development, can you, in science?
Right.
That's the way research goes, is a piece field. Yeah. And the more you open up, the more questions are posed.
Yes.
So if you fail to find this Higgs boson, what are you going to do afterwards if that experiment fails?
Well, we've still got the challenge as to why the W and the Z and the photon have the masses they've got, and why the theory that fits them. The work we've done at LEP has shown that that theory works to an accuracy of getting better than 1 part in 1,000 now. And it only has one free parameter in it that isn't already measured. And that parameter at the moment is the mass of the Higgs boson. We can't quite constrain it and say where it is, we just say we need it. Now, it's needed from experimental reasons that there is something there like the Higgs boson. If it isn't the Higgs boson, then what is it? That's an even bigger question. That's even more interesting, actually, if we don't find it. But we think that nature tends to be as simple as it's reasonable to be, and we probably will find the Higgs boson. But we could be wrong.
And all this takes money and international collaboration, and that's one of the big things about CERN, isn't it? It's an international effort.
Well, CERN, the thing that's worked up at CERN, you noticed on the picture that there were actually 4 intersection regions.
Yeah.
Each of those intersection regions has an experiment just like ours, slightly different techniques. It's run by, each of the experiments is run by something like 20 or 30 university and national groups. And each of those groups is doing its very best to beat the others, so that the Aleph experiment has got Imperial College in it, and Royal Holloway. And the Opal experiment I'm in has got University College and Queen Mary in it. Both of us are collaborating with people from all around the rest of the world. Yeah. We're all the best of friends, but we want to beat them to discover the Higgs boson.
I'm afraid that on that competitive spirit we're going to have to end the programme. It only remains for me to thank our guests, Natalie, Amy, Simon, Ian, Rosanna, Tim, and of course our special guest, David Miller. Thank you, David.